A second method that can be used to find the area under the curve is Simpson's rule, which uses parabolas to find the area under smaller segments of the curve. And then again, you're going to add up all of those estimates to find the total area. With Simpson's rule, when you use the parabola, you're actually looking at, in essence, two intervals at a time. So here I've got this curve y equals f of x in blue. It's subdivided into these different intervals. And then again, we're looking at two of these segments at a time. To simplify things, if you were to imagine, with it being a parabola, it's going to be symmetric. If you were to center it at the origin, so you'd have that perfect symmetry, you can integrate and find the area of the shaded region to be h over 3, where h is the distance from the origin. And then it's y naught, so that's that left y value, plus 4 times the middle y value, plus y sub 2, which is that right y value. So that gives you the area for two of these subregions. If you were to continue this process all along the curve, two of these subintervals at a time, you would come up with Simpson's rule. And please keep in mind here that I am greatly simplifying things. If you want to read through a little more in depth about how this process works, please see the book. They do a very good job going in depth with it. But Simpson's rule says that to find the area under the curve as an approximation, it's delta x over 3, where delta x is going to be the distance here of these intervals. And then it's y sub naught plus 4y sub 1 plus 2y sub 2. And it follows this alternating pattern of 4, 2, 4, 2, all the way down to y sub n. Now, in case you're wondering where the 2 comes from, when here it was y sub naught plus 4y sub 1 plus y sub 2, that y sub 2 is going to be the left endpoint for the next two regions, so it'll get doubled, hence the 2. So in this case, you just need to remember that 4 and 2 pattern when you're working it. We are going to look at an example here. Let me scroll down. It says, the design of a new airplane requires a gasoline tank of constant cross-sectional area in each wing. A scale drawing of a cross-section is shown here. The tank must hold 5,000 pounds of gasoline, which has a density of 42 pounds per cubic feet. Estimate the length of the tank by Simpson's rule. So here we're given this cross-sectional view. We're told that the horizontal spacing, that's going to be our delta x, is 1 foot. So this 1 foot is going to be our delta x. And then it gives us the different values for y. So we have y sub 1 up through y sub 6. Before I get into Simpson's rule, I want to talk about the volume of this tank. So the full volume of the tank can be found by taking the amount of gasoline that it holds here, or the weight of the gasoline, which is 5,000 pounds, and dividing it by the density of the gasoline. So that's 42 pounds per cubic feet. If I divide this out, it's going to give me the volume of the tank, and I'm going to leave it in a fraction form. It'd be 5,000 over 42, which you could reduce to 2,500 over 21 cubic feet. So that's the volume of the tank in cubic feet. We can also think of the volume of the tank in another way. So the volume of the tank can be found by taking this cross-sectional area, which we're going to find with Simpson's rule, times its length. So we know the volume of the tank is 2,500 over 21 cubic feet. We're going to use Simpson's rule to find the cross-sectional area, and then we'll be able to divide those to find the length. So finding that cross-sectional area, again, we're going to use Simpson's rule. Our delta x is 1, so we have 1 over 3. And in this case, it's y naught, which is 1.5. And then we do that 4-2 pattern, plus 4 times 1.6, plus 2 times 1.8, plus 4 times 1.9, plus 2 times 2.0, plus 4 times 2.1, plus that last one is just a 2.1. If you add up everything inside the brackets, you're going to get 33.6. So let me scroll down a little bit. So we have 1/3 times 33.6, which is going to give us 11.2 square feet for our cross-sectional area. So to find the length, it's going to be the volume divided by the cross-sectional area. So the volume is 2,500 over 21 cubic feet divided by 11.2 square feet. And if you divide that out, probably I should have used approximately instead of equals, you're going to get about 10.63 feet.